Welcome to S.A.ENG.COLLEGE GATE coaching video. This is Nithya Assistant Professor, Department of ECE at S.A.ENG.COLLEGE. The topic is Fourier transform, sampling theorem and its application. So what is Fourier transform? Fourier transform is used for transforming the time domain signal into the frequency domain signal. It is a tool used for breaking the waveform into an alternate representation which is characteristics as by sine and cosines. It shows that any waveform can be represented in the form of the weighted sum of sinusoidal functions. So it is also defined as, it is a mathematical tool for analyzing the frequency of the signal, frequency analysis of the signal. So Fourier transform is mainly used for transforming a non-periodic time domain signal, non-periodic function in time domain into frequency domain. So the next we'll move on to the mathematical representation of Fourier transform. So the mathematical representation is f of omega, which is equal to minus infinity to infinity f of t e power minus I omega t dt. Here f of omega is the frequency representation, frequency domain representation of the signal, and f of t is the time domain representation of the signal. So what is the difference between the Fourier series and Fourier transform? Fourier series is used for converting, it is mainly used for the periodic signal, and Fourier transform is mainly used for the analysis of non-periodic signal, that is aperiodic signal. So now we'll see the conditions for existence of Fourier transform. Fourier transform exists the signal f of t which is satisfy three following conditions. The three conditions are, first condition is it should be absolutely integrable. Absolutely integrable means it should be less than infinity. And second condition is it should have minimum, that means finite number of discontinuities. And third condition is the function must have finite number of maxima and minima. Only when these three conditions are satisfied, then the signal Fourier transform will exist for that signal. So next we'll move on to the inverse Fourier transform. So inverse Fourier transform is used for recovering back, that is converting the frequency domain signal into time domain signal. The formula is f of t 1 by 2 pi minus infinity to infinity f of omega e power j omega t d omega. So here this inverse Fourier transform is used for converting the frequency domain signal into time domain signal. Next we'll move on to the mathematical problems, examples. So the first problem is sketch the following waveform function in the time domain and calculate it by using the Fourier transform. Here the function given is f of t which is equal to 3 between the interval from minus 2 to 2. So from minus 2 to 2, the value of the function is 3. For that we need to calculate the Fourier transform. So we know the formula f of omega which is equal to minus infinity to infinity f of t e power minus I omega t dt. When substituting f of t which is equal to 3, then after integrating this will give e power minus I omega t by I omega. So after integrating, substituting the upper limit and lower limit will have e power 2 I omega minus e power minus 2 I omega. Now we are rearranging this expressions in order to get the sinusoidal functions. So rearranging this, 3 is rearranged as 6 by 2. So now it is e power j omega, so e power I omega minus e power minus I omega divided by 2i, that can be represented in the form of the sine function sine 2 omega. So the second example problem is find the Fourier transform of the signal e power minus at. So when substituting x of t which is equal to e power minus at, then after integrating this u of t exists, u of t which is equal to 1 So 1 into e power minus at e power minus j omega t dt. Then integrating this will give e power minus a plus j omega of t. So after integrating this, we have to substitute the upper limit and lower limit. So e power t exists between from 0 to 1, the value is 1 only from 0 to 1. So the limit changes from minus infinity to plus infinity. Because of the presence of u of t, it is changed from 0 to infinity. When substituting the limit, e power infinity is 0 minus, then e power minus of minus, then e power minus 0, which is equal to 1. So 1 divided by a plus j omega. Next we will see about the properties of Fourier transform. So the first property is linearity. Linearity states that addition of two signal in time domain which is equal to the addition of the signal in frequency domain. H of x, h of g of x, both are time domain signal whose Fourier transform is equivalent to the addition of their Fourier spectrum, Fourier domain signals. And the second property is scaling property. So scaling property states that when a constant get multiplied to the time domain signal, then their frequency transform which is equal to their frequency domain will get divided, the constant get divided in the frequency spectrum, and it is multiplied by 1 by modulus of, that is the constant, the modulus of constant get divided. Then the next property is time differentiation property. Time differentiation property states that differentiation of the time domain signal, that is f means that is f of t time domain signal whose differentiation which is equivalent to multiplying j omega to the frequency domain. So the next property is convolution property. Convolution property states that convolution of the two time domain signal which is equivalent to multiplication of their frequency spectrum. And similarly, multiplication of the two time domain signal which is equivalent to the convolution of their frequency spectrum. So the next property is frequency shifting property. So shifting in frequency, that is f of omega is the frequency domain signal. Frequency domain representation of f of t is shifted by omega naught. Then there equivalent is f of t, that is time domain signal, is multiplied by e of, that is e power j omega naught t. Then the next property is time shifting property. So here the time domain signal gets shifted by t naught time. So whose Fourier transform which is equal to their Fourier spectrum is multiplied by the exponential form e power minus j omega t naught. Next we will see about the problem based on the properties of Fourier transform. Gate question. The Fourier transform of x of j omega of the signal x of t is given. The time domain signal is given. They are asking the Fourier transform. So here the duality property. Here the first they applied the duality property. Duality property state that x of t whose duality, that is x of t that whose that time domain signal whose Fourier transform, that is applying duality, that is x of omega, when x of t, then the transform duality, according to duality it is capital X of t, here capital X, here small x. Then this one, so the spectrum of t, that is whose duality is 2 pi, and this one is small x, here it is capital X and here it is small x of minus omega. These two lines state the duality property. So now our problem, we know that in the previous slide I have shown you that e power minus at u of t whose Fourier transform is 1 by a plus j omega. Already we saw that. So similarly e power minus a, instead of t modulus of t, for that the Fourier transform is 2a square plus omega square. Here when substituting a equal to 1, so in this when substituting a equal to 1, we'll have e power minus modulus of t and 2 into 1 which is 2, then 1 square is 1 plus omega square. So applying the differentiation property, differentiation and frequency property, x of t, that is Fourier transform as x of omega. The differentiation of frequency domain is d by d omega of x omega, whose equivalent, which is the time domain signal, is multiplied by small t. So now our x of t is e power minus modulus of t u of t. This is our x of t. So 2 into our x of t, which is j d by d omega, and our x of omega is 2 divided by 1 plus omega square. So the next one is, so next, when differentiating this 2 by 1 plus omega square will have minus 4 j omega divided by 1 plus omega square whole square. So applying the duality property to this expression 2, the expression 2 is t e power minus modulus of t u of t and Fourier transform per minus 4 j omega 1 plus omega square whole square. Our second duality property is capital X of t, and which is 2 pi small x of minus omega. We have to apply this duality to this expression. So now, so this side it is capital X of t. So here this one is capital X of, this one is capital X of omega. So we need to replace this omega by t. So now this omega is replaced by this omega is replaced by t, and here also the omega is replaced by t. Now it is equal to 2 pi and this one 2 pi, and here it is small x of minus omega. So this one is small x of t. So now this t is replaced by minus omega. So here, so instead of t we have to write omega, and e power minus, instead of t we have to write omega. So now when strike outing both the side, it is 1 time and this one is 2. So our question is to find t divided by 1 plus t square whole square. So move this 2j to this right hand side. So pi divided by, when this one comes this side, it is 2j omega e power minus modulus of t. So the equation t divided by 1 plus t square whole square, for that the Fourier transform is pi by 2j omega e power minus modulus of omega. So next we'll see the sampling theorems. So what is sampling theorem? Sampling theorem is used for converting the analog representation of signal into the discrete, that is digital signal. So here the analog signal can be defined as converting the analog signal into a discrete form by taking the frequency sample. This conversion is done by taking the sampling frequency, which should be greater than twice the maximum frequency content of the signal. So the signal will be represented, can be represented in its sample and can be recovered back completely when the sampling frequency is greater than 2 FM. This Fs is the sampling frequency and this FM is the maximum frequency content of the signal. So the next we'll see about the sampling block diagram, its output waveform. So this is the block diagram of the sampling process. So the input signal, the analog signal is given, and here the periodic signal sequence get multiplied to the analog signals. So the periodic signal sequence, here it is the pulse train or impulse sequence. This is multiplied to the analog signal in order to convert that analog to the digital sampled output signal. So here this is the analog input and this one is the sampling pulse, which is used for, then this, when multiplying these two, it is converted to this form. So the analog will be converted to the discrete form. This process is said to be sampling theorem. And next we'll see about the applications of sampling theorem. So the application, sampling theorem used in many applications, and the first one is it is used for maintaining the sound quality in music recording, and this is used for the conversion of, as I said before, it is used for the conversion of analog to digital signal, and third one is it is used for the speech recognition and pattern recognition, and it is used in the modulation and demodulation process, and it is used in the sensor data evaluation system. It is used in radio and radar navigation systems, and the last one is digital watermarking and biometric. So these are the applications of sampling theorem. So next we'll see in the next session. Thank you.